Hello everyone, welcome to the lecture series of 8085 Microprocessor. This is lecture number 12. Today we'll be doing some instructions of 8085, but before doing that I'll just show how we can run this 8085 on a mobile app. There are many mobile apps which are available, so I'm taking this as a very simple program, like write a program to store 12H in register A, 13H in register B. So this is the program, memory location. So MVI A 12H, the 2 byte instruction, MVI B 13H, 2 byte instruction, then HLT. These are the hex codes. Okay, 3E12 06 13 776. So these are the hex code, and these are the memory location. Now let us see how we can enter this particular code using a mobile app. In the previous lecture, we saw some data transfer instructions. Now we will see some next category, that is the arithmetic instructions of 8085. Now before starting with the instructions, we must note down some points. Arithmetic here means addition, subtraction, increment, decrement. We'll see the instructions, but we'll note down some points first. Except for INR and DCR, increment and decrement, all the arithmetic instructions, they have some assumptions. The very first assumption is that register A is one of the operand. Okay, so we cannot perform addition, subtraction without A. So A should be always there for any of the addition or subtraction operation. Then second, result is always stored in register A. So when we are adding the contents of two registers, one of the register is A, so the result is stored in A, and the contents of the other register apart from A is not modified. So suppose if we are adding register A with register B, then the result is stored in A, but the contents of B, they are not modified. Then the fourth point is all the flags are affected. Okay? With all the 5 flags which we have. So if a carry is generated, then a carry flag is set. If the result is 0, 0 flag is set, and so on. And regarding this INR and DCR instructions, they do not affect the carry flag. So carry flag is not affected by the INR DCR instruction, but all the other flags are affected. Now let us see the instructions of 8085. The first one is the, you can say, the first arithmetic instruction is add R. So add R is a 1 byte instruction. It adds the contents of register A with the register with the contents of the specified register R. So here R can be any other register. It can be A, B, C, D, H, L, any one of the register here. And here we see all the flags are affected. So add B, add C, these are the examples. Let us see, suppose if I write this add B. So add B means A equal to A plus B, and add C, it means A equal to A plus C. So this is regarding the add instruction. This is a 1 byte instruction. Then next instruction is ADI data. So this data is a 8 bit, or we can say 1 byte data is there. The instruction is a 2 byte instruction. It adds the contents of register A with this 8 bits or 1 byte data which is specified. All the flags are affected. Let us see the example. Like if I write ADI 15H, so it means A equal to A plus 15H. So this data is stored in A. Suppose if A contains, let us assume A contains 2, and I write ADI 0, suppose not 02, suppose 03H. So this will result in A equal to A plus 03. So A is 2 and this will go 5. So A will become 5. Then we have SUBR. So SUBR is also a 1 byte instruction. It subtracts the contents of A from the specified register, whatever the specified register R is, and all the flags are affected. Like here if we see this particular instruction, so if I write sub B, so sub B means A equal to A minus B, and in this case also all the flags are affected. And one more thing, the carry flag, it acts as the borrow flag. In case if A is less than B and we are subtracting, so a borrow will be generated. So this carry flag is acting as a borrow flag for this particular operation. Then we have a SUI. Okay, SUI means subtract immediate. SUI, it is a 2 byte instruction. It subtracts the contents of register A from the given 8 bit or 1 byte data, and all the flags are affected. Like here, suppose if I write here, in this case if I write SUI 12H, so this means A equal to A minus 12H. So H means hexadecimal number. So whatever the data in A, it gets subtracted from 12 and the result gets stored in A. Next we have these two instructions, INR and DCR. So INR is a 1 byte instruction and it increments the contents of the given register by 1, and DCR is also a 1 byte instruction. It decrements the contents of the given register by 1, and it can be performed on any register. And in this, as we have seen, carry flag is not affected, rest all the flags are affected. So just for example, suppose if register B, if it contains suppose 05H, if I write INR B, then the content will become 6. It increments the content by 1. Now suppose if I write DCRB, it will decrement the content by 1. So INR DCR, this is a 1 byte instruction. It can increment decrement the contents of any register by 1. So this was regarding the arithmetic instruction. Okay, now let us write a simple program based on the arithmetic operation. So here we have write a program. WAP means write a program to store 15H in register A, 19H in register B, and add their contents. So we need to store 15H in register A, 19 in register B, and we have to add their contents. So we know for storing the data we use MVI A 15H. Okay, then this is a 2 byte instruction, so I have to leave one gap. Then this is 19H, then I have to add. Okay, So for adding A and B, we have the instruction add B, and the result gets stored in A, and then finally halt, HLT. Now I will copy out the hex code from the hex code paper. So MVIA is 3E, then next is 15, 15 comes here. MVIB is 06, next data is 19. Add B, the opcode for add B is 80, and halt is 76. I will execute this program on Jubin simulator. You can also do it on either using Jubin simulator or one which I have shown in this video using the mobile app. Now first of all, what answer we will get when we are adding these two numbers, what answer we are expecting. Let us see what answer we would be expecting, because this is hexadecimal addition, not normal addition. So 15, I write this 15 in this particular binary notation, hexadecimal code notation. Sorry, this first of all, the code for 1, so 1 is 0001 and 50101, then 19, so 19 is 1001, sorry, 1 will come first, so 0001 is 1 and 9 is 1001. Now I add this number, so 1 plus 1 is 0, carry 1, this will become 1, this will become 1, this will become 1, 1 plus 1, 0, carry 1, so this is 1, 0 and 0. So answer is 0010, which in hexadecimal is 2E. So answer what we would be getting is answer should be 2E. So let us enter the program and check it. So I have opened up the simulator. So I won't go in this particular mode, I will go in the simulator, this kit mode. So this is the kit mode, this is the kit. Okay, so reset is already there. Okay, then set 8000, then INR. So this opens up. So here the code, the first code is 3E, so 3E, then INR 15, okay, then INR 06. I can even use the enter key, then INR 19, then INR 80, then INR 76, then again INR. Now this is how I enter the code. Now to execute, I go to reset, go 8000, and then execute. Okay, the program has been executed. Now I have to check the result. As we know, the result should be 2E in register A. So I check the content of register A, and it is of course 2E. And as I see, B remains 19. The content of B are not changed. So this is how we execute the program. You can do it on your mobile app or even on any of the simulator. The next category is the logic instructions of 8085. Logic means ANDing, ORing, XORing, complementing, etc. Now except for CMA, that is complement the contents of accumulator, all the logic instructions, they have this following assumptions. The first is register A is one of the operand. Okay, so we cannot perform any logic operation without A. Then result is always stored in register A. So when we are performing any logic operation, the result gets stored in A. The contents of the other register are not modified, they remain as they are. In every logic operation except this CMA, carry flag is always reset. Okay, carry flag is always reset, while sign 0 parity, they are modified according to the result. And this AC flag, it has some different effect on different logic instructions. So we'll see in when we are studying that particular instruction. Then the CMA, this instruction does not affect any flag. So these are some of the assumptions. Now we will study those instructions. The very first logic instruction is ANAR. So this is a 1-byte instruction. It logically ANDs the contents of register A with the specified register and stores the result in register A. So here we see for AND operation, AC flag is set and carry is of course reset. The example is ANAB, ANAC. So what this instruction does is actually, we can see here, if I write this ANAB, ANAB means what? A equal to A and logically AND with B, and the result is of course stored in A. So we can logically AND the contents of A with any other register. Okay. uh, then we have A and I. A and I is AND immediate. So AND immediate with the 1 byte data. So this instruction is 2 byte of 2 byte. It logically ANDs the contents of register A with the given data byte and stores the result in A. Of course here also AC flag is set and carry is reset. So here suppose if I write the instruction like ANI 1919H, so this is A and 19 and the result gets stored in A. Then similarly we can have this ORA. So ORA instruction is a 1 byte instruction. It logically ORs the contents of register A with the specified register and stores the result in register A. Similarly we have ORI data. So ORI is a 2 byte. Of course whenever I comes, that is immediate, whether it is MVI, ADI, SUI, ANI, ORI, this all instructions are 2 byte instructions. This instruction ORI, it logically ORs the contents of register A with the given data byte and stores the result in register A. Then we have the XRA. XRA is a 1 byte instruction. It logically XORs the contents of register A with the specified register and stores the result in register A. So we have these examples XRA B, XRA C, etc. Then we have XRI. XRI is actually a 2 byte instruction, XOR immediate. So it logically XORs the contents of register A with the given data byte and stores the result in register A. Then finally we have CMA. CMA is a 1 byte instruction. It complements the contents of register A. So complementing means what? 0 becomes 1, 1 becomes 0. And here it is only for register A. We cannot complement directly, cannot complement the content of any other register than than A. So we can only complement A. So if thus there is some data in B and we want to complement that data must be transferred to A, complement, and then transfer it to again B. So no flags are affected in this particular case. So you can also see some examples, like suppose if we have in register A, suppose if we have the data 2A, suppose, and if B contains 1C and we want to logically AND, suppose I am logically ANDing the contents, so what the result I am expecting is 2 is 0 0 1 0 and A is 1 0 1 0. Then I have 1 is 0 0 0 1 and C is 1 1 0 0. So if I logically AND this, so this is 0, this is 1. For AND operation we know that when both the inputs are 1, then only output is 1. So this is actually 0, this is 0, this is 1, because both the inputs are 1. This is 0, this is 0, this is 0, this is 0. So answer is 0 8. So when I logical, this is for AND operation. Now suppose if I do the same thing for OR operation, with the same thing OR operation, for OR even a single input is 1, output is 1. So this is 0, this is 1, 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 this is 0, this is 0. So the answer is 3E. So for operation OR operation we get the answer as 3E. Now what happens with XOR operation? For XOR operation we know that the output is high when odd number of inputs are high. So this is 0, this is 1, this is 1, this is 0, this is 1, this is 1, this is 0, this is 0. So this is the answer. So answer is, this is 3 and 6. So for XOR operation the answer would be 3 6. Now in case if I complement the content of A, register A, I want to complement, suppose, okay. So complement operation is only for single register A. So if A is 2A and I write complement CMA A, so here whatever data I have, this 0 becomes 1, 1 becomes 0, so 1 1 0 1 0 1 0 1. So 1 1 0 1 is actually D and 0 1 0 1 is 5. So this 2A becomes D5 if we complement. So that's all for this particular lecture. In this lecture we have done arithmetic and logic instructions. In the next lecture we will do some branching instructions and some more instructions. Thanks for watching.